Hello everyone, my name is Matthias from EPFL in Switzerland, and I'd like to thank you very much for taking interest in my work on cantilevers for atomic force microscopy. I want to start out by giving you a little teaser of what the device I'm going to present can do. If you have ever used an AFM before, chances are that you complained about how long it takes to get an image. It is usually pretty slow going, as you can see here. On the right side, you can see what we achieved in this work. A very similar image in just 16 seconds. I'll get back to this later, as soon as I've given you a bit more background information. I'll be starting by presenting the actual device. First, its concept, and the way we fabricate it, then the way we use it on our AFMs. Finally, I'll explain how it can improve a current AFM technique, allowing us to image much faster. So this is an image of one of the cantilevers. As you can see, it has a wide base that works as an actuator for the narrower cantilever attached to it. To bend the cantilever, we make use of thermal expansion. We run an electric current through the gold meander to change its temperature. Here is an exploded view of one such cantilever. The main structure is made of 3 layers. A thick orange polymer core sandwiched between 2 blue thin films. The polymer is viscoelastic and introduces material damping, ensuring that the cantilever has a low quality factor, something that I will get back to later in the talk. Finally, the cantilever features a sharp silicon tip, something that is primordial in AFM imaging. The sharper the tip, the better the reconstruction of the surface which is being probed. I will now walk you through how such cantilevers are fabricated. We call this the tri-layer process. We start with a silicon wafer with a silicon nitride thin film, typically less than 100 nanometers thick. Next, we use 2 lift-off steps to pattern the gold heater and add an aluminum cover on the wire bonding pad. We then spin coat the polymer, a BCB solution commercially available under the name of cyclotene. This polymer can be used for wafer bonding and can also be dry etched. The coated layer is typically a few micrometers thick. We also spin coat this polymer on a second wafer. Then we bond the 2 wafers together. Note that this forms a tri-layer structure in the middle, composed of the polymer sandwiched between 2 silicon nitride thin films. Next, we etch the silicon of both wafers in KOH, and we do this until a thin silicon layer of about 15 microns remains. This we will use to create the tips. To do so, we make a mask out of silicon oxide through lithography and wet etching. This mask is under-etched, again in KOH. We end up with a tri-layer membrane in the middle, a silicon chip on one side and a sharp silicon tip on the other. To finally obtain a cantilever, we pattern its shape through lithography, then dry etch through the tri-layer structure. This also opens an access hole to the bonding pads at the same time. These pads are connected then to a small PCB through wire bonding to electrically contact the heater. The PCB has a connector on the backside and can be plugged directly onto a custom-built holder. This holder is compatible with a Brooker multimode head and can thus be directly used on such an AFM. After being inserted into the head, the pins are lowered and contact the cantilever heater to the AFM controller. The head is then attached onto the AFM scanner and is ready to be used. Now, these cantilevers were developed for a specific imaging mode, off-resonance tapping. This mode is also known as peak force tapping or pulsed force AFM. To illustrate how it works, we'll consider a cantilever and a scanner holding a sample. On the right, we'll plot the distance between the tip and the sample versus the force applied on the tip. This force is proportional to the deflection of the cantilever. In off-resonance tapping, the sample is moved up and down a few thousand times per second. When it gets close to the cantilever, the tip snaps onto the surface and is then pushed up until reaching a maximum force. The sample then moves back away, and adhesive forces retain the tip for a bit, until it snaps off and goes back to its initial position. This procedure allows to obtain a few thousand force distance curves per second. Different parameters can be extracted from the curve, such as the peak force, the surface adhesion, the stiffness, and the energy dissipated during the cycle. These give valuable information about the mechanical properties of the sample. Now let me go back to the video I showed you in the beginning. It shows the image acquisition in this off-resonance tapping mode with a commercial cantilever on a Brooker multimode AFM. Here, each line of the image consists of 500 pixels, and we are obtaining 2000 pixels per second. If we want to obtain at least one force curve per pixel, it follows that we can scan a maximum of 2 lines per second. So it takes a few minutes to get the entire image. On the right, we image the same sample with the cantilevers presented in this work. I'll now explain how we can get a similar image in just 16 seconds. So in conventional off-resonance tapping, the sample is actuated below the scanner resonance and thus limited to a few kilohertz. This corresponds to the couple of thousand force curves we can get per second. In our case, we use the integrated actuator of the cantilever to actuate the device rather than the sample. Since the cantilever resonates at much higher frequencies than the scanner, we can operate it much faster, at tens of kilohertz. This allows us to obtain data at more than 10 times faster rates, and thus to get images quicker. The operation looks like this. A sinusoidal current flows through the heater, modulating its temperature and bending the cantilever down and back up. This free motion is recorded. We call it the background. In the presence of a sample, the cantilever will stop as soon as it touches the surface. The force curve is then obtained by subtracting the background from the actual measured motion. When imaging at such high rates, some new problems can turn up. One of them is cantilever ringing. When the cantilever snaps off the surface, it rings at its resonant frequency. The amplitude decays exponentially, and the ring down time depends on the quality factor of the cantilever. If the lever is still ringing when snapping onto the surface for the next cycle, all the energy is dissipated into the sample and can damage both the sample and the tip. To avoid this, we need to keep the off-resonance tapping period long enough to ensure a complete ring down. This is where the polymer core of our cantilevers comes in handy. Since it introduces viscoelastic damping, the ringing energy is dissipated much faster than with traditional high Q factor cantilevers made of silicon or silicon nitride. Alright, to conclude, I wanted to present an image obtained with our cantilevers that shows some of the mechanical properties that can be extracted in off-resonance tapping. The sample is a composite of glass fibers and epoxy. The topography is shown on the left. The blue image in the middle shows that the glass fibers are much stiffer than the surrounding epoxy. On the red adhesion channel on the right, we can see some sticky patches on the glass fibers. This means that some epoxy was likely smeared onto the glass fibers while polishing the sample. To sum up, we present a cantilever with an integrated electrothermal actuator that can push off-resonance tapping rates to tens of kilohertz. The polymer core ensures a low Q factor and fast ring down between cycles. The sharp silicon tip ensures sharp images. With a custom cantilever holder, the probes can be used directly on commercial AFMs. And with that, I'd like to thank the people who contributed to this work from the Laboratory of Bio and Nanoinstrumentation at EPFL, my co-authors Mustafa Kangul, Santiago Andani, and Nahid Hosseini, as well as my advisor, Professor Georg Wagner. Thanks also to Dr. Coades and Professor Michaud from the Laboratory for Processing of Advanced Composites for providing us with the glass and epoxies composite sample. A big thank you also goes to the staff of the cleanroom facilities at EPFL. And finally, I would like to thank all of you for your interest and your attention.